My name's Ethan Meitz, and I'm a PhD student at Carnegie Mellon University, and I'm here with my co-presenter, David Krasowska, who is a PhD student at Northwestern in computer science. This work was also a collaboration with Wanchan Lee at NVIDIA and Pat McCormick at Los Alamos. And today our presentation is about a library that we've written called cuNumeric.jl, whose goal is to make writing distributed, multi-GPU, multi-node programs easy. The high-level goal of our package is to take code that you have written as a user and scale it across whatever system you have access to, whether that be a single CPU, a multi-GPU system, or a supercomputer, without you actually having to change any lines of code at all. So code that runs on a single CPU should also run on multi-GPU as well as your supercomputer. And the kind of motivation for this is that if you're a domain scientist, it's relatively easy to implement your physics in a high-level language like Python, MATLAB, or Julia, but it is much harder to then take that code and scale it across whatever compute resources you have access to. Often the skill sets of physics and high-performance computing are very separate, even though these physics codes often scale well on computers. So we're trying to bring these two worlds together, make it so the physicists can use these high-performance tools. So the kind of core type that is enabling all of this magic is called the ND array. This is very similar to a Julia array. We are attempting to implement it so that it is just a drop-in replacement for a Julia array, except that it can represent data across multiple devices. The key differences right now between the ND array and a Julia array are that operations are broadcast by default, so even if you don't put the dot operator, it's just going to broadcast your operation. Slices are always views, so we kind of get rid of those extra allocations that are by default in Julia. And then just like with any GPU array, scalar indexing is really bad, but in this case it's extra bad because you also have to go look up which device your data might be on. So it's incredibly slow to do scalar indexing on these arrays. And just kind of a sneak preview to kind of prove to you that this is indeed possible, we've implemented the Gray-Scott 2D partial differential equation, and this is the get diff for converting that from a Julia implementation to a cuNumeric implementation that runs on multiple GPUs. And you can see the only lines of code we've really changed are just the initialization. So we changed from a Julia array to an ND array, and that was all we had to change to get this running. Looking a little bit deeper at the core technologies that enable this library, we are building off of many years of research by NVIDIA as well as Stanford, who've created the Legion and Realm libraries, and NVIDIA has implemented this legate framework. This legate framework, NVIDIA's goal is to implement all of these Python libraries. So their most mature library is called cuPyNumeric. It implements the NumPy API, but they also have plans to implement SciPy, Pandas, sklearn, and all of these other libraries that are very common in the Python ecosystem, and then run them on whatever hardware you have access to. And this is nice and all, but this is JuliaCon, and I like writing my research code in Julia. So David and I asked the question, like, wouldn't this be nice to do in Julia? And is there something we can do with Julia that is not actually possible in Python? And David will talk a little bit more about that at the end. And just even more specifically, we are focusing only on this cuPyNumeric component. So this is kind of mimicking the NumPy API. So we will have access to things like matrix multiplication, as well as most unary and binary operators. Going a little bit deeper into how legate is actually working, your program flow might look like this, and this is just using calls from like Python API that you might be familiar with. And the kind of one key thing to note here is that we're mixing all these different libraries. So like you have an HDF5 read, you're using cuNumeric to do adds and matrix multiplications. And all this just works because the underlying data structure, the library making all this possible, has the same data format, and that is legate. So when you run your program like this, each of these functions is implemented as a legate library. So these are not actually calling the typical Python library. This is a bespoke implementation using the legate framework, and each of these functions will emit a legate task, which are then further broken down into smaller parallel tasks that are automatically converted into a DAG by the runtime when this determines your execution and program order. And one important thing here is this is all implicit. The user does not, the end user, the one running this API, does not actually have to tell legate what the data dependencies are. Legate is just going to figure this out based on how you've written your program, And then the final thing is we take this, or legate takes this DAG and runs it on whatever your target hardware is. So that was just a little bit of how legate is working. If you have more questions on how the details of this library work, definitely ask at the end or come up to us afterwards. But now getting into what David and I have done. So the existing software stack that we are building off of looks like this. There's legate, legion, and realm, which are all implemented in C++. And then NVIDIA has gone and implemented a cuPyNumeric in C++. So this is taking legate and implementing things like matrix multiplication, dot products, outer products, all that kind of thing. That is all in C++. And then they have, in typical fashion, bindings to that library, and then the user-facing Python API, which in this case perfectly mimics the NumPy API. We're doing this all in Julia, and our software stack looks like this. So we have C++ bindings directly to legate, as well as bindings to this cuPyNumeric. So we not only have broken out cuNumeric, but we also have access to legate bindings as well, which will enable us in the future to write libraries in Julia that use these legate primitives. Most of what we're talking about today is with cuNumeric, except for one slide that David will talk about, where we use legate to actually run CUDA kernels CUDA kernels with the legate stack. So this is the high-level software stack. But now let's actually get into some results, convince you that this library does in fact work, because it does sound like a little bit of magic. At least I thought so when I first started working on this project. So the first thing we tried to do was Monte Carlo integration. The technical details of this are not that important, but the main point is that this is an embarrassingly parallel problem, so it should scale perfectly. This should be something that's really easy for legate to handle. The two tasks really that this has to do is generate a bunch of random numbers and then apply some function to all those random numbers and take the mean. So the kind of code looks like this. This is the syntax for our library, and the weak scaling of this for 8 GPUs, which is what we've had access to. We, in the future, would like to scale across multiple nodes, but we didn't have access to those resources for this presentation. But we basically see perfect scaling for both cuNumeric.jl as well as cuPyNumeric for this problem. And that's good because this is an easy problem. If we actually look at the throughput for these different kernels, though, we see a little bit of stratification. Specifically, cuPyNumeric is a little bit less performant than the Julia wrapper that we've created. And one thing to note, the y-axis here, it's not exactly gigaflops. There's some constant factor that we don't know. And then we also ran CUDA.jl on just one GPU to kind of see the throughput and treat that as our benchmark. So we are getting similar throughput to CUDA.jl and then scaling perfectly as we add GPUs. And we think that this small difference between the Julia and Python libraries is because cuNumeric is directly calling into the C++, whereas cuPyNumeric, the Python library, actually has several layers of Python that it's going through before it ends up calling into the C++ library. The next kernel we looked at was matrix multiplication. If we can't do this, we probably shouldn't have come here to talk about, or come to JuliaCon and present our work. The syntax looks like this, and just one caveat. You cannot generate float 32 random numbers at the moment, so technically you have to typecast from float 64, but the syntax we hope to have soon will look like this, and n was not actually 10, it was much bigger than that. So the weak scaling for this, cuPyNumeric and cuNumeric.jl, again, scale perfectly, and David wrote a bespoke kernel with CUDA.jl that uses multiple GPUs that also scales fairly well. If we look at the gigaflops for this again, we see that we're basically maxing out the throughput for our GPU. So we scale perfectly, and we're maxing out the memory bandwidth of our GPU. So this is all we could really hope for. So matrix multiplication is working fantastic. And now I'll hand it off to David to talk more about some complicated examples, as well as some cases where cuNumeric did not work as well as we had hoped.
All right. So thank you, Ethan, for the great introduction. So cases where it might not work. We started with Gray-Scott heat diffusion, which is the same git diff that we showed earlier. The issue with this is we ran into this great error right here. We were not able to execute this, right? Why aren't we able to execute this? And it clearly says we're out of memory. And by just enabling a forced garbage collection, we were able to achieve Gray-Scott to run. So each object included in slices are treated as temporary objects within our cuNumeric framework. So why does the Julia garbage collector not collect these objects? So this is a bold claim, but this is what we found that's true, and what other libraries actually do as well, is foreign memory is not automatically garbage collected within the Julia ecosystem. So the garbage collector just sees foreign memory as just a pointer, and the base Julia garbage collector relies on the notion of heap heuristics. How much heap saturation do you have present within your program before the garbage collector is invoked, right? So we are using CUDA, we use the profiler, and we look at something that we expect to be 40 megabytes in cuDA.jl. It's a 10 million array element. We take a heap snapshot, and Julia just sees it as 184 bytes of data. And you could clearly see that in the profiler too. So this claim that garbage collection heavily impacts performance here, and you could see by this graph, this is basically, we're trying to force the garbage collection, and we're doing a fixed interval iteration count within our application. So we will iterate through 1, 3, and 6 iterations, and you can see here, as we decrease the frequency, we get better and better performance that converges to cuPyNumeric, which we're treating as our baseline. So going back on what AMD GPU and CUDA.jl do, these existing backends really, they know the rough memory footprint the objects will take whenever the object's constructed. So they track all these GPU allocations, they manually invoke, based on some heuristics, the garbage collector, and they have a try-catch block to basically prevent out-of-memory errors like we saw in the pop-up box that I showed earlier. And the issue with our library is we don't know exact sizes at construction of these objects. The legate runtime may deduplicate objects or duplicate them in some way based on performance optimizations. And another thing that we can't do is we can't recover from an out-of-memory error within the mapper. So that's not great. So we have to be very conservative if we create automatic heuristics, which is what we did. We have automatic heuristics that enables us to run the Grayscott heat diffusion without manually placing the garbage collection call. And you can see here, we do slightly better, and the red line is our cuNumeric.jl with the new garbage collection heap heuristics versus our old method. On 1 and 2 GPUs, we are performing better and matching what cuPyNumeric does. However, when we scale for some reason, which we're looking into future work, we don't get exactly what we need to. So this is great that we have an automated way of running a garbage collector, but the issue here is we just don't scale as well as we need to. So another aspect is you may have seen that there's a dotted line of floating point 32 theoretical performance on this Grayscott heat diffusion application. We're pretty far from it. And we started to look into this, like why are we so bad relative to the peak theoretical performance? So we decided to rewrite a test application of the same application in a Julia library, implicit global JL. This is a stencil-based PDE solver that runs on multi-node NVIDIA and AMD GPUs with minimal code changes. And their library performs extremely well. And so we started analyzing this. And one of the big things that our framework doesn't do is kernel task fusion. There's a high degree of overhead in the sense that if you launch multiple operators, operator by operator, every single one of those operators has overhead. So this is work done by the Legate team at ASPLOS 2025, and they basically got a 1.8x speed up on average throughout a diverse set of applications and up to 10x. So that 10x is a huge difference for just doing kernel fusion, and that's roughly the same gap, that performance gap that we have. It's about a 10x difference. So this led us into what if we do some sort of fusion Of course, that entire backend support is a lot of work, so we decided to start with just utilizing CUDA.jl and write custom kernels and see how that registers and weak scales with our runtime. So the ability to register custom CUDA.jl kernels with our runtime, basically, this is a normal CUDA.jl kernel without any modification. You could initialize our cuNumeric arrays, so just initializing the data. And then you could launch and compile this is a kernel add, so it's a very simple thing. The thing is, whenever you launch, you have to specify inputs and outputs. That's just a part of our heuristics. In order to build the DAG implicitly, we need to figure out what the inputs and what the outputs are. In the future, we'll probably do some sort of LLVM pass in order to automate this potentially. I don't want to promise, but it's great. You could have a custom CUDA.jl program and it works within our framework. There are some caveats, but I'll get into this example. So this is a Grayscott heat diffusion, but a one-dimensional example, and it's just a subset of the kernels within that larger application. And you can see the syntax here is just the kernel, and we achieved, like CUDA.jl, they also support their own custom kernels, and they have an operator by operator syntax. So our library does that, and you could see the difference. The blue is the fuse kernels that I was just presenting, and then the red was the prior when you unfuse, doing operator by operator. There's a substantial difference in the sense of you could get a performance benefit by fusing kernels, and that's what we saw with the prior work with the legate team. And that's also what you see with the CUDA.jl library. You could get a performance benefit by fusing kernels. So to summarize this work, operator invocation overhead really just limits performance scalability. And we have ongoing, like this is an ongoing work. As you could tell, I did 1D instead of our 2D example. Multi-dimensional support is not prevalent yet within the custom CUDA registration. So there's ongoing backend enhancements to support the multi-dimensional cases and also multi-GPU execution. The reason we have a bar graph is this is only on a single GPU, unfortunately, right now. But by the time we release this package to the public, this should be able to scale multiple GPUs. And then you could tell that CUDA.jl versus our package, CUDA.jl is performing better on a single GPU, so why use our package, right? The backend overhead is amortized as you increase the number of GPUs. We're doing the same data dependency analysis that enables the multi-GPU execution. So you could get that for free once we get that supported. So that same backend cost will be there even if you scale across multiple GPUs, so it gets amortized. So some of our conclusions, you could do minimal code changes to your Julia CPU code, and it runs across multiple GPUs, multiple nodes, and you could see we get good weak scaling for some of the examples we showed. The ability to register custom CUDA kernels with the CUDA.jl framework backend. And then our next support steps is basically supporting a wider range of custom CUDA kernels. Like I mentioned, there's some caveats. However, we're still working on towards getting everything supported. Hopefully by like September, we want a beta release. And another thing we want to do is improve the robustness of our application. Right now, just installing things are pretty messy. So like as a user at JuliaCon, you might run into some problems trying to install our application. And then another thing we want to do is enhance the integration with the Julia runtime and abstraction interface. At the current moment, there is a huge problem, I would say, is we're treating this library as a C++ FFI interface. We're just calling in to C++ mainly. As you could tell with one of the results that Ethan presented with Monte Carlo integration, we were performing better than the Python interface. The Python interface has more integration, And we'd like to do more integration to use some of the Julia runtime heuristics and stuff like that. So that would be a future work to explore. How do we integrate it more with Julia? Another thing, multi-node systems. All our results have been single node. And the goal is to test this. We haven't tested it yet for multi-node support. In theory, our entire software stack should just automatically make this work. However, of course, nothing works as you hope. And then, yeah, with the garbage collection heuristics, the goal is to make that, as you could tell, with like 4 GPUs and 8 GPUs, it was falling off. That's not great. So we want to fix these GC heuristics. And some of the things, in order to do this, we would need better information about the programs when things get out of scope, that kind of thing. The issue is we're relying on, the runtime gets notified of an object's like lifetime based on our deconstructor calls within garbage collection. So having better GC heuristics will reduce false dependencies of objects within our runtime. So that will enable you not to run out of memory. That's a huge thing. And then automatic kernel fusion is the experimental work that I was talking about, the legate team. And that would be really cool to implement in the back end. And then operator by operator automated kernel fusion, then just a general abstract array cuNumeric.jl program will just magically work. And you'll have a better scaling that we see, and the performance gap will be mitigated. So yeah, we're looking for a September beta release. Hopefully we could get there. I think we're on good track. There's a lot of features that we're still just developing and engineering through this. I believe we started this project late December. Yeah, late December is when we started this. And it's made fast progress. And I'm excited to hear feedback from this community about this project. And I'd like I mentioned, to integrate more with the Julia language runtime stack. Because right now we're treating it more like an FFI interface with minimal Julia code. So how can we integrate and tightly couple the Julia runtime stack with our runtime stack? So thanks to our collaborators at NVIDIA and also Los Alamos that made this. And then thank you for making the introduction, Ethan. Does anybody have questions?
Awesome talk. As someone working on Dagger.jl, which is a related library, I find the ability to kind of implement your own parallel algorithms as a directed acyclic graph very powerful. That's what we're doing with Dagger. Mm-hmm. I'm not sure if I saw it in the presentation, but do you have any examples of how you actually do that with legate.jl, or do you have that integration, and is there like kind of a plan to make that like a first-class interface?
Yeah, right now, like we don't have that as a first-class interface within legate.jl. Do we have plans for that? I would say so, but it's engineering effort at the moment.
Yeah, because like legate.jl is a separate library from cuNumeric.jl right now, and we basically just implemented the things in legate that we needed to launch the custom CUDA kernels. But I do think it would be really cool if you were able to write legate applications, legate libraries in Julia using legate.jl. That's just more developer time, but it is definitely possible.
Yeah, because basically how legate works is you as a, let's say you're a library developer, right? For every operator that you want to support within your library framework, you just register that task to the legate runtime. You register also what the dependencies for that specific task are. So you have a notion of what are the dependencies, and you register that task with the runtime, and runtime knows about it. It knows how to schedule it. It knows what the dependencies are. But that's all internal C++ code within the legate runtime.
Great talk. For anybody who's been in the computer science community for a while, you know there's nothing new under the sun. That's a principle of computer science. 25 years ago, we had a parallel MATLAB thing going on, and we learned very quickly for the need for kernel fusion because we implemented one kernel at a time, and it killed us. So that's an old notion.
Operator invocation overhead is killing us in
it's
that
the
example.
same story.
Yeah.
A challenge that I want to put out is, and this is not how one starts, but I'm not sure anyone ever gets there, is, once you've got a small list of things you can do, matrix multiply, parallel Monte Carlo, dot products, maybe there's a list of 10 basic things. You get those, and then what comes next? I mean, I've always wanted to see a world where people who write serial code, just to do anything, not Grace Scott, but whatever, the 99.9% of things that people really do, how do you get parallelism there? And I'm not expecting an answer, but I'd love for you to think about it.
Yeah, I mean, the overall goal of legate is implicit parallelism, right? Extracting out all independent partitions within any of your tasking operations. However, like you mentioned, it could be any arbitrary code that might not have any parallelism characteristics. And how do you extract that out, right? That's a good question. I don't have a good answer for. If there's not parallelism that exists in the independent task graph, yeah.
Hey. Yeah, I had two quick questions. So one is, so it's building on an NVIDIA project. Have you also looked at how performance is on the CPU compared to how you would usually write CPU code? And does it run on AMD GPUs at all? And then the other question I had for the GC part, did you look at how the Python side solves that?
Yeah, so the first question, the CPU thing, we have not benchmarked it, but this library and the whole legate stack also works for CPU code. We were more interested in the GPU stuff, though. What was the second question again?
Python ref counting. So the reason Python doesn't have this problem, and they didn't have to implement any specialized heap heuristics for cuPyNumeric, is because Python has a ref counter for external memory references, right? Whenever something's out of a scope or anything like that, then the deconstructor is called because there's no references to it, right? The Julia garbage collector is, I guess it's a mark and sweep algorithm based on heap heuristics and heap saturation. Because our external memory references don't saturate the heap at all, right? Everything's just an 8-byte pointer, no matter if it's 20 terabytes or 2 megabytes, whatever it is, Julia doesn't see any of it. And that goes into my point of having more tightly coupled integration for stuff like this, and includes the registration of the ability to notify Julia of the sizes of external memory references. That would be potentially useful for libraries like AMD GPU, CUDA.jl, and our library, because and Dagger.
The second question was AMD support, right? So this does not support AMD right now. As you can imagine, NVIDIA is not super interested in doing that. They're not going to stop you, however. So Legion and Realm are completely agnostic. It would just require someone to go and implement these things for AMD. And I think there is some things in Legate that are specific to NVIDIA that David can maybe talk about.
Yeah, so right now the entire Legate stack is just NVIDIA specific. So what Legate does versus what Legion is. So Legion is the entire heterogeneous scheduler, and it requires a notion of a user writing a mapper, right? Legate automatically writes a mapper for the different operators and data dependencies. It has its own heuristics and stuff like that. But those heuristics are specific to NVIDIA GPU devices to do its partitioning in an optimal way, and especially the cuPyNumeric and stuff like that. Behind the scenes, it's all just NVIDIA specialized kernels to implement all these different operators. So in theory, this could work, especially the shortest path to getting this working with multiple devices is if the CUDA.jl registration using AMD GPU registration or something like that. But you would have to create custom mapper heuristics in order to get this support within Legate. And that will enable different types of GPUs, but NVIDIA does not want to support this, unfortunately.
So technically possible, but a lot of developer time.
Yeah, and there's no support for it.
All right, so since we are very close to lunch, and most of my questions have already been answered, I want to thank the speakers again, and we will reconvene at 1:30.